Welcome back, everyone. Argentina has been expanding its role in space technology, and one of the most significant areas is satellite Earth observation. At the center of this effort is CONI, the National Commission on Space Activities, which has been launching satellites equipped with advanced imaging sensors. These spacecraft provide critical data for agriculture, environmental monitoring, and resource management. In today's video, we will examine how Argentina's satellites work, the principles of hyperspectral imaging, the organizations involved, and the future challenges and opportunities of this technology. Subscribe now! The starting point is understanding what Earth observation satellites are designed to do. Traditional satellites capture imagery in visible light, similar to photographs. They can also use multispectral sensors, which detect a handful of bands beyond human vision, such as near-infrared. Argentina's new focus is hyperspectral imaging. Hyperspectral sensors divide light into hundreds of narrow bands across the electromagnetic spectrum. Each material on Earth reflects and absorbs light differently, creating a unique spectral signature. By capturing this detailed spectrum for each pixel, scientists can identify crops, detect soil properties, monitor pollution, and even distinguish between similar plant species. The satellites essentially act as orbital laboratories, measuring reflected sunlight across a wide wavelength range. CONI has developed several satellite missions under the SEOCOM and Sabia-Mar programs. The SEOCOM satellites, launched with support from SpaceX using Falcon 9 rockets, are equipped with radar sensors that operate independently of daylight or weather conditions. Sabia-Mar, currently in development with Brazil's space agency AEB, will carry optical and hyperspectral instruments for monitoring oceans and land. The hyperspectral sensor works by passing incoming light through a diffraction grating or prism inside the satellite instrument. This splits the light into its component wavelengths. Detectors then record the intensity of each wavelength for every ground pixel. Processing software converts the raw spectral data into usable maps that can be analyzed for agricultural and environmental information. So, to appreciate why hyperspectral data matters, it's useful to compare it to older satellite systems. Landsat satellites, which are run by NASA and the US Geological Survey, capture multispectral data with about 10 to 15 bands. Sentinel satellites, from the European Space Agency under the Copernicus program, provide similar multispectral imaging, but with just a slightly higher resolution. These systems have been extremely valuable for global land monitoring. Hyperspectral imaging can use anywhere from 100 to 400 bands. This gives far more diagnostic power, allowing scientists to detect really subtle differences that multispectral satellites might miss. For instance, identifying nitrogen stress in crops or mapping invasive species becomes feasible with hyperspectral detail. Argentina's involvement means that such data is generated locally and, importantly, can be applied directly to regional challenges. The processing chain behind hyperspectral imaging requires substantial computing resources. Raw data collected by satellites are transmitted to ground stations operated by CONI in Córdoba and Buenos Aires provinces. The data are then calibrated to remove sensor noise and atmospheric effects. After calibration, algorithms are applied to extract specific information. For agriculture, spectral indices are calculated to estimate chlorophyll content, soil moisture, or disease presence. For ocean monitoring, algorithms can track chlorophyll concentrations, turbidity, and harmful algal blooms. Researchers at the University of Buenos Aires and the National University of La Plata collaborate with CONI on developing these processing models. Publications in IEE Transactions on geoscience and remote sensing have detailed how Argentine scientists refine these algorithms to improve accuracy under local conditions. The agricultural sector in Argentina stands to gain significantly from satellite hyperspectral data. Argentina is one of the world's largest exporters of soybeans, corn, and wheat. Farmers and agribusiness firms often rely on field sampling or drone imagery for crop monitoring. However, these methods are limited in spatial coverage. With satellite hyperspectral data, large areas can be scanned on a regular basis. This allows early detection of crop stress, enabling timely fertilizer adjustments or pest control. Companies like Bayer Crop Science and Syngenta already use remote sensing data globally, and they have shown interest in incorporating hyperspectral analysis into their advisory platforms. The ability to predict yields with higher precision benefits both producers and international markets. Beyond agriculture, hyperspectral imaging actually plays a role in monitoring deforestation, wetland health, and water quality. Argentina contains parts of the Gran Chaco forest and vast river systems, such as the Parana. Environmental agencies must track land use changes and detect illegal deforestation. Traditional multispectral imagery can show broad patterns, but hyperspectral data provides much finer discrimination. The underlying physics of hyperspectral sensing is based on spectroscopy. Every molecule interacts with light in a characteristic way. Chlorophyll strongly absorbs red and blue wavelengths while reflecting green and near infrared. Water, on the other hand, absorbs strongly in certain infrared bands. By comparing the full spectrum of reflected light to known laboratory spectra, analysts can determine what materials are present in each pixel. This requires building spectral libraries. Argentina is compiling libraries of local soils, crops, and vegetation types. Researchers at CONICET, the National Scientific and Technical Research Council, are leading this effort. Their spectral library enables faster and more accurate classification of satellite data. Without these reference libraries, hyperspectral data would remain just abstract numbers. Hyperspectral satellite instruments face quite a few engineering challenges. They must achieve high spectral resolution without becoming too heavy or power-intensive. The diffraction gratings and detectors must remain stable in the thermal and radiation environment of orbit. To address this, instrument developers use lightweight materials and radiation-hardened sensors. CONI collaborates with INVAP, a major Argentine technology company, to build satellite components. INVAP has experience designing nuclear reactors and radar systems, and it applies similar engineering rigor to space instruments. Reports from Nature Photonics have described how miniaturized hyperspectral sensors are being tested worldwide, and Argentina's engineers are adapting such designs for Sabia Mar to ensure reliable long-term operation. Hyperspectral data volumes are large, often hundreds of gigabytes per day from a single satellite. This creates challenges in transmission and storage. Argentina's ground stations must have high-bandwidth links to receive the downlinked data. Cloud platforms are increasingly being used to store and process these datasets. CONI has partnered with European organizations and the European Commission to align data formats with Copernicus standards. This interoperability ensures that Argentine data can be combined with European Sentinel data or NASA's planned surface biology and geology mission. Joint projects with the European Space Agency and NASA increase scientific value and avoid duplication of effort. Case studies illustrate the practical applications. In 2023, researchers at the University of Buenos Aires used SEOCOM radar and hyperspectral drone data to map soil moisture variability in the Pampas region. Their findings, published in Remote Sensing of Environment, showed that hyperspectral indices predicted yield variability more accurately than traditional multispectral methods. Comparisons with older technologies highlight the advantages. Weather satellites such as NOAA's GOES series provide valuable data, but with coarse resolution and limited spectral range. Synthetic aperture radar, as used in SAOCOM, is excellent for soil moisture and surface roughness, but does not capture spectral details. Hyperspectral imaging complements these by providing biochemical information. A combined system that integrates radar, multispectral, and hyperspectral data yields a more complete picture of land and ocean processes. Argentina's multi-mission approach shows foresight in building a balanced Earth observation capability. Similar strategies are being followed in Europe and India, where ISRO has planned a hyperspectral imaging satellite called HISIS. Looking toward the near term, by 2026, Sabia Mar is expected to be operational with its hyperspectral payload. Early results will likely focus on agriculture and coastal monitoring, providing datasets to farmers and environmental agencies. In the medium term, by 2028, Argentina could integrate hyperspectral data into national crop insurance and food security programs. Longer term, the data could be used for climate models, carbon monitoring, and international collaborations. Satalogic deserves special attention. Founded in Argentina and now operating globally, Satalogic builds small Earth observation satellites. In recent years, it has expanded into hyperspectral imaging. Their satellites are designed for frequent revisit times, meaning they can capture the same location daily. This differs from large government satellites, which may revisit every 16 days. The combination of CONAI's national programs and Satellogic's commercial fleet positions Argentina uniquely. Government and private sector satellites together provide data coverage that is both broad and frequent. According to IEE Spectrum, Satellogic's approach could transform how industries access hyperspectral data by lowering costs and increasing availability. Universities play a vital role in training specialists who can interpret hyperspectral datasets. The National University of Córdoba and the National University of San Martin run remote sensing programs that include laboratory courses in spectroscopy and data analysis. Students work with real satellite data through CONI partnerships. This ensures that when new satellites are launched, there is already a trained workforce ready to apply the data. One limitation of hyperspectral imaging is cloud cover. Since most instruments rely on reflected sunlight, persistent cloudiness can obscure the ground. This is why radar satellites like SEOCOM remain essential companions. By combining radar and hyperspectral data, analysts can fill gaps caused by cloud cover. Another challenge is cost. Building hyperspectral satellites is more expensive than standard multispectral systems. Maintenance of calibration also requires regular ground truth campaigns, where scientists collect samples in the field to validate satellite readings. Funding from the Argentine government and international partners remains crucial. Economic instability can threaten continuity of programs, but the long-term benefits in agriculture and environment often justify the investment. Another area where hyperspectral satellites are beginning to contribute is mineral exploration. Argentina has significant reserves of lithium in the so-called lithium triangle, shared with Chile and Bolivia. Traditional geological surveys rely on field mapping and core samples, which are time-consuming and expensive. The broader implications extend beyond Argentina. If successful, the Sabia Mar mission and commercial satellites from Satellogic will contribute to global open data initiatives. Agricultural monitoring in Brazil, fisheries in Chile, and forestry in Paraguay could all benefit from shared hyperspectral datasets. International organizations such as the Food and Agriculture Organization of the United Nations rely on such data for regional planning. Argentina's leadership in this domain enhances its scientific reputation and creates export opportunities for satellite technology and data services. It also reinforces South America's role in global space activities, which have traditionally been dominated by the United States, Europe, and China. As we conclude, Argentina's satellite Earth observation program demonstrates how a mid-sized country can advance by focusing on specific niches, such as hyperspectral imaging. Through the work of CONAI, INVAP, Satellogic, and collaborations with universities and international agencies, Argentina is building a strong foundation. The technology is complex, requiring detailed spectroscopy, advanced detectors, and powerful processing systems, but it is already proving its value. Farmers, environmental regulators, and international scientists are finding practical applications. By 2026, the first major hyperspectral datasets from Sabia Mar will be available, and the following years will show how well Argentina can integrate these into decision-making systems. Thank you very much for watching. Please like and subscribe.